statistical approach and other mathematical approach for investigation. When the classes are of arbitrary shape. Challenging issue is when the classes are of arbitrary shape. Classes are of compact nature, it becomes easier. Now I will explain the judicious integration of this, rough fuzzy interpreting, example of integrations, general updates, this has been done. Today I will explain in those applications to image segmentation, pixel classification, granular thresholding, basic, then I will go towards video tracking. Okay, because video is nothing but image sequence of frames. So unless you understand image processing, you cannot work on the video tracking. So different tracking problem, situation, and how to form the granules. One-dimensional granule, two-dimensional granule, three-dimensional spatio-temporal granule. Then new concept of dark filter, handling occlusion problem. These are all new areas. Then if I get time, one application in bioinformatics, how to use in short. Then last part I will move to the challenging issues of deep learning and other issues for the research issues problem, but it is currently hot topic. So I will explain rough fuzzy clustering and uncertainty analysis. Here I will show how the class exactness in terms of granules are defined. So granules are used to define exactness in a class. What is mean by exactness class? And fuzzy set enables handling overlapping partition. Rough set deals with vagueness and incompleteness. And if we can make it judicious integration, we will have improved performance and faster than fuzzy clustering. So wherever fuzzy clustering has been done for the past 4 decades or so, this clustering will be much superior to them. So in the literature, fuzzy sequence has been widely used for the last 4 decades. So many publications have. So now this will all overcome those. Now what is the basic concept? As I mentioned to you, this is my cluster in granular domain. This is my lower approximation. This is alpha that I explained yesterday. That means for this region, I have no doubt about the samples as far as the belongingness to this cluster is concerned. Only my doubt comes from this portion. So here I am, is one. So integration of the concept of fuzzy sets and lower approximation of will have. So what will our intuition says? For this, because fuzzy clustering is expensive. You have to get all membership values, you have to keep them, storing them, it is expensive. Why we make it expensive? Because I do not want to lose any information till I reach the end. Then I can throw it away. But otherwise, if I lose it before, then I am not unable to get the doubtful samples corrected till I reach one. So it is at the cost of money. Now I say, since I have got lower approximation, for which I have no doubt, why should I pay here fuzzy membership? I make it 0.1. 0. Only I put fuzzy membership of this. So that will drastically reduce my completion time and also retain my efficiency. That's a very simple concept. So while fuzzy sets enable handling overlapping partition, rough set deal with vagueness and incompleteness in class definition. Here rough sets helps me in defining the exactness of class. Here exactness of class is the lower approximation. Very simple concept. So we assign membership value for any pattern of this class is 1 if the objects of it belong to lower approximation. That means either and while this membership any value fuzzy for those in bounded region. Assign higher weight for objects in lower approximation and compared to bounded region. So while I am updating the centroid, because in a clustering you always update the centroid. So when I updating the centroid, I give more weightage for this. I give less weightage for this while computing. But when I computing the other classes centroid, I do this class lower approximation has no impact because it is belonging definitely to this class. So the only boundary has impact to compute centroid for other classes, but with less weighting. So assign higher weight for objects in lower approximation as compared to boundary region while computing the centroid of the own class. Influence in computing centroid own and other class for lower approximation on the own centroid, for boundary on all centroid. It's clear? So when I am computing my class 1, I only consider upper and lower, but while I give more weightage for the lower than the boundary. But while computing for others, then this lower has no impact there. Therefore, each clustering is represented by a triplet. Cluster prototype, fuzzy boundary, and a crisp core. In case of hard clustering, hard C means that means 0 or yes or no, there the cluster is characterized by only cluster prototype. If you have worked in clustering, you must have worked in clustering. No? So if you look at if you have a hard clustering, every cluster is characterized only by the centroid. In case of fuzzy clustering, centroid and boundary. In case of rough, fuzzy, another component comes, this core. And this is the property of rough clustering, that it is union, or if I take the union of all upper approximation of all clusters, it will be the universe. If you take the intersection of the lower approximation between two clusters, it will be empty. If you take the intersection of the lower of one class and the boundary of one, that is also empty, because there is a disjoint. For every values of I and k, if it belongs to boundary between two classes, then this and intersection will be non-empty. Similarly, for membership value will be 1 for all elements belonging to lower approximation, and any value between either 0 or 1, or including 0 and 1 fuzzy, only belongs to boundary. This is a characteristic of this property. So what is given basically philosophically? It is making a balanced mixture between restrictive partition is hard clustering. You have no choice, you go to there or not. In case of fuzzy clustering, it's called descriptive. Every pattern can go to every class with a matter of membership. So rough fuzzy give a balanced mixture between two restrictive partition, therefore it is faster than fuzzy clustering, better uncertain handling part of this. So wherever fuzzy clustering has been used since its inception in 1972, up to so much 50 years, this will be superior to them. So let us give some example of now magnitude resolution segmentation, and I use this typical DB index, Dunn index, because it is unsupervised, and I also use the beta index. First I use the beta index. The DB index basically, if you look at this, you take two patterns together, two classes together. You compute their this variance and the distance. In case of DB index, this variance should be less and distance between the two classes should be more. Therefore, larger the value of DB index, better is the segmentation. On the other hand, here distance is in the numerator, so distance should be more, and the variance, maximum variance among the two classes is the denominator, so it should be low. So larger the Dunn value, larger the value is higher. So for DB index we will want low value, for Dunn index you want larger value, and beta index it should be again larger value. Difference is that beta index you do not consider two classes together. Every class we just consider individually. So these are the three types of measures. Now let's consider the brain MRI image, which is collected from Advanced Medical Research Unit, Calcutta, famous institute. We use SCM, FCM, RCM. RCM means crisp lower, crisp upper. And this is another one where crisp and upper both are fuzzy. But in our case, crisp is lower and upper is fuzzy. Just permission. And look at this for all these images. DB index maximum in the lowest value, Dunn index maximum value, beta index maximum value of the proposal. And if you look at the FCM, it is higher, but if the competition will be more. RCM, second one. So individual value of delta, that is the difference between first and membership and second membership. It was initially 0.145 because at the beginning, every pattern has a possibility to go into more than one class. So difference between first membership, second membership will be less. But as you go for iteration and we are making segregating, that will be high. So we consider C equal to 4, background, white matter, gray matter, and semi-possibilian. Now let's see some data. This is for different other classes. This is the same result you are getting. This is always best performance compared to all. More information you are going to come on this. Now competition time wise you see results. For DB index, this is the lowest, all for lowest. Look at this one. For fuzzy RCM, hard Siemens is poorest. FCM is then RCM. Now if you go to Dunn index, highest in everywhere. Competition time wise, beta index, that is also. Everywhere it is maximum. So quantitatively, visually, it is shown that it is extracting better information. And if you go by the then execution time wise, minimum is hard Siemens because it is very fast. Fuzzy is the maximum because you want to work complete membership always. Rough is better than slightly taking more time. You are completing lower crisp, upper crisp. This is the situation. Now this shows how with iteration difference between first membership and second membership of pixel is increasing difference. Initially they are almost zero difference. That's why they belong to 45-degree angle. Majority. Now after iteration they have done this. Difference between first highest membership, second highest membership. So pictorially if you go inside you can see how for any pixel is belonging to a class, first membership and another class with second membership, the difference is getting expanded because you are making a more cluster with iteration. So far this gives an image partitioning by pixel classification. I take a pixel, I mention it by clustering. Now there is image segmentation by gray level. This is another approach that without knowing the clustering, I partition the gray level. There I take the local information, global information, depending on that you better resolution. I hope you understand segmentation. Both are unsupervised, but one is going by the pixel by classification, another is without considering the pixel by pixel, you go by the thresholding of the gray level. One. If I have gray level say 0 to 31, which level will determine the threshold for class 1, which level will determine the level for class 2 and so on. So here I use the generalized rough image entropy because that measures reflect the amount of gain or the amount of uncertainty as conveyed by the definition of rough set X with the given definition, and it is measuring the information incompleteness gain, measure of incompleteness of knowledge. So I would like to minimize the incompleteness. Yesterday I explained the rough fuzzy entropy. What did you remember? You didn't remember anything. I explained the roughness entropy, rough fuzzy entropy indicates the amount of incompleteness in the universe. Given that set definition X in the granular domain, which measures the amount of incompleteness knowledge. So if we measure the incompleteness knowledge, my intention will be trying to minimize the incompleteness in order to segregate the image. So I will minimize that. And also I have taught this rough set, rough fuzzy set, fuzzy rough set, and fuzzy rough set. So amount of complexity increases, but at the same time you perform improvement. So image ambiguity measures. What is image ambiguity? There are two types of. One is region in J level has a boundary, just for reminding, refreshing. Fuzzy boundary is taken care of by fuzzy set theory, and roughly disable level, roughly disable pixel. What is roughly disable level? 6 is close to 5 and 7. 7 is close to 6 and 8. So there is a notion of rough resemblance of a gray level. Similarly, rough resemblance of pixel, every pixel tries to attain an intensity value which is adjacent, which is similar, close to its neighboring. If there is an abrupt change, there you get an edge. If there is no abrupt change, it is a homogeneous region. So if you pass it through high pass filter, then abrupt changes will be detected. If you pass it to low pass filter, the uniform regions will be detected. So that's why smoothing is equivalent to low pass filtering, and high pass filtering generates your edges, edge bound. The one is the sharp change. Sharp change means it contributes to high frequency. No sharp change means contributes to low frequency. So fuzzy boundaries of region, rough resemblance between nearby levels, rough resemblance between levels. That will be taken care of by the rough fuzzy entry. That I explained yesterday, the reminder. Now, in the rough set theory framework, what can you do? The object sensitivity, you think independently. I can consider every object consisting of two parts, or lower and upper. I can simply concept it. And in case of fuzzy set theory, every pixel can go to any class with a matter of degree. That's what you do. So, object can be described as rough set upper and lower approximation. Fuzzy set theory, any region, edges, feature, they do not themselves feature any definition, so they can be represented as a fuzzy subset of the image plane. That's the true notion. And what is grayness ambiguity, spatial activity? Grayness ambiguity means whether pixel is considered to be black or white. And spatial ambiguity means I ask the question, what is the boundary? So that is concerned with the spatial ambiguity. In the earlier case, it is obviously whether pixel is considered to be yes or no. Whether machine understands, because machine understands only black and white. So I will consider, therefore, when I compute the grayness ambiguity, I made the indefiniteness to fuzziness as well as granularity in gray level. And indefiniteness is concerned with gray value of individual pixel and group pixel. But whereas it is concerned with the spatial location. This is a difference. Here, I only consider the indefiniteness of the pixel or a group of pixel with respect to its intensity value. But here I consider both intensity value as well as its location. So obviously this will give you a better result. Obviously. Now I will use this entropy as I defined yesterday. Now next question, how to define the gradient? So for beginners, I can define many ways. Say 1 and 2 dimension. This is my gray level scale. I can define the gradient 1 to 3. Crisp gradient 1 to 3, 3 to 5, 5 to 7. I call it non-overlapping one dimension. Very simple, and it is least expensive. I can have 1 to 3, 2 to 4, then 4 to 6, 6 to 8. I call it overlapping one dimension. That means I am taking more information. I can have fuzzy granule overlapping. So depending on your problem, I can go from simple one to harder than hardest. Okay? Now, similarly in the two-dimensional scale image, I can have this crisp granule. Non-overlapping two-dimensional granule. 3 by 3 mass, 3 by 3 mass, 3 by mass, discrete. I can have overlapping granules. So I more extract information. Then I can have so one level 2 dimensional granule, and now you can have it bell-shaped membership function. I'm not drawing here, it is difficult for me to draw. Bell-shaped membership function where you've got 2-dimensional fuzzy granule. Okay, understand? Now let's give an example. I am computing entropy of the LMC using rough fuzzy set. Here membership function is fuzzy, so the set is fuzzy, granules are crisp. Simplest case is, this is crisp, this is also crisp. But I am showing one level of uncertainty handling, where boundary is considered to be fuzzy, but granules are considered to be crisp. Now, how do you compute the difference here? If I would have, no side topic here. If I would have considered fuzzy entropy, which we defined in NPL college in 79, there are no concept of granularity. So it is smooth on the fuzzy set. No green or red. So every pixel corresponds to one, every intensity corresponds to one unique membership. In case of fuzzy set, where there is no granularity, every intensity corresponds to only unique members. But in case of granularity, since we have come, the intensity of the same pixel depends on the grade scale, on the granule where it belongs, because it is determined by green and red. Previously the value was here, for example this intensity, in case of fuzzy set, in case of not fuzzy set, the membership value depends on the granule. If it belongs to this granule, the membership will be green, lower and green. Now this additional information helps you in improving the details of the process. So fuzzy rough set, mean value of pixel entirely dependent on its own granule. Whereas in rough fuzzy set entropy, mean value is dependent on its one-dimensional granule to which it belongs. It is clear? So now see the result. So I take a membership value, define membership value, I shift it over the scale, and I see where this rough fuzzy entropy comes minimum. Whether it's a fuzzy entropy or rough fuzzy entropy, it gets minimum. Because I want to minimize the entropy. So difference is basically of effect of fuzzy granules. So if I do no granularity, then it boils down to fuzzy entropy. Now see there are three types of images: baboon image, brain MRI image, remote CT. We have different types of histograms. Histogram, you can see that it is taken under poor illumination. This is laboratory. So you see that we have considered W equal to 6 as per Weber's law, 1 to 6, 2 to 7, which naked eye cannot discriminate. So W equal to 6 granules. The simple granule in the linear scale, 1 to 6, 2 to 7, 1. And see there one. Proposed rough fuzzy entropy, fuzzy entropy. Look at the difference. More clear information. Here is not that much evident, but these two you can see the difference. Fuzzy entropy, fuzzy entropy. This is also reflected when you compute the beta index. What is the beta index? Beta. Okay. You said there are 50 such MRI images, images, where is images of galaxy, images of brain MRI, images of nematodes. You see that red indicates fuzzy entropy, green indicates proposed fuzzy entropy. Except 3 cases, this is 1, 2, and 3 cases. Everywhere green is superior, either blue is superior. As far as beta index is important. So significance of using concept of a granule is evident. Now, I'm just skipping because observations are minimizing the because now the question comes whether if I make the set crisp and granule fuzzy, one, how it be changing. So definitely these are all indications. I'm not going into the mass details. If you look at this beta index, beta value is improving. Here also beta value is improving when we make the third cases. Now, I'm just skipped it over. So far we have considered granules of equal size. 1 to 6, 2 to 7, 3 to 6. Now next question comes, what will happen if granules are of unequal size? That is the real, more practical problem. Definitely it will give you a better result. So that is what I want. So how to do it? We consider formation of unequal granules. That can be done many ways. One way is very simple. You make quantity decomposition. What is the quantity decomposition? If you know anybody quantity decomposition, you take an image, make it a 4 quantity. Every quantity you compute maximum intensity, minimum intensity. If you want to see the homogeneous region for granule, so difference should be less. So put a threshold. If the difference exceeds, then you split it again 4. Till you split it again 4 quadrant, till in that condition, maximum minus minimum is less than. Very simple approach, one of the approaches. It's called quantity decomposition. So unequal can consider grain levels in quantity decomposition. Similarity criteria, the difference between max and mean grain levels. If a granule is greater than a threshold, we have chosen. And this threshold is chosen half of the interquartile range. What is the interquartile range? You split the segment, histogram into 4 parts. And you take that level up to which the 3/4 of the pixels have belonged. That is called interquartile range. So you take the half. That is one of the guidelines. How do you just say the threshold? So you take the histogram and see up to which level 3/4 of the pixels belong. So you take L1 is the gray level up to which mn by 4 pixels, and there are L2 is the gray level up to which 3/4 of the gray levels belong. Interquartile range is L2 minus L divided by 2. Now look at the image. Quantity decomposition as I explained. You know this lady? Image? Lena, not Lina. Lina is an Indian name. Lena. And Lena was basically a call girl. But if you look at now, this image has been banned. Now, why this image becomes so popular for image compression and what? You know? Can you suggest anything? That is beautiful. That's why? No. Because this is image where you have got different characteristics. This is a sharp contrast image. This is a blurred image. This is 3-dimensional shoulder, 3-dimensional. This is texture. In one image, you get smoothness, edgy boundary, your blood one, and then the 3-dimensional effect, texture. One of the criticisms of pattern image processing, as I mentioned the past day, that any algorithm, if you develop, it cannot work, doesn't work with any other. That is still one of the criticisms. So here at least you reduce that criticism. You develop an algorithm and see whether it works better here, which can take care of smoothness, edginess, texture property, 3-dimensional property, and so on. So given this Lena image, if we split it, this is an example for different kinds of quadrant. Smaller size quadrant, larger size quadrant. For example, this is my lower approximation, upper approximation. So I split an image in special quadrants. Of course, the quadrants granules are of and consider them as granule. So each granule would be of different sizes and shapes. Whenever it is a blurred region, granule will be bigger. When it is an edgy region, the granule will be smaller. So given this threshold, so I find a threshold and I form this granule. Threshold is determining the size of the granule. And I minimize. Now look at this video tracking I am moving towards. This is one of the frames. Hello, please go ahead. One of the frames, three video screens. See, you see that tiny here, all cars, human being moving. Original Otsu's threshold is a very popular threshold in. You get this result. It is a rough entropy with 4 by 4 granule, simple. 6 by 6 granule, rough fuzzy entropy with crisp set and 6 by granule, and this is the proportion. See that here you can get these cars best detected. Human beings also best detected. Now you may ask me questions, how do you just quantify them? Let's consider beta index variation from frame to frame. It was in one frame only. I get the same data. Now in sequence of frames, so you have to check whether it is working same for the other frames also or not. Otherwise you may think that I am cheating you, just give you one frame and show you. So beta frames when you see iteration wise, look at this. This is proposed one. You want to have one. You want to have larger beta for every frame, and beta should be consistent. Here you see that beta is not consistent. This is called rough fuzzy with 4 Y. Sometimes increasing, decreasing, sometimes increasing, decreasing. So it is no way good. Sometimes you can track, sometimes you cannot track. Similarly, this one, larger value, Otsu's threshold, but it is consistent. The green one, 6 by 6. But this is the proposed one. Higher value, consistent. Now I can see the homogeneous granules of unequal size reduce the formation of Fourier segment. Therefore, reduce the abrupt change of index value over frames. This is for beta, you have BB index, same, proposed one comes later, done. Now I put this. So I have shown it pictorially and also. Now I show you for tracking. So this is my detection segmentation done in image domain, spatial domain. But for tracking, I need to make temporal domain segmentation also. Temporal, that means the difference domain. Difference domain, I have to again segment and then I take in union. This is a very simple way. But that may not work for complicated images. So let's consider the simple image first. So temporal segment. What is temporal segmentation? It's for 3-point segmentation. Given an image, you compute the 3-point segmentation, and now merits of unequal size over granule with the fixed granule. So tracker signifies segmented output. Now this is the same one of those frames I take where the cars show up there. This frame I take. Okay. Six by 6. See, sometimes it is tracking, sometimes it is expecting. Let's see the what's block. What's the working sometimes? Can you see now? No, but here it is coming. Here it is coming. Let me make it forward. coming. Huh? There is a problem. If I can show the video, there is coming. But when now we will make it a PPT. Yeah, now it's working. Yeah, it will work. But if we make it PPT mode, it is working. Right, so mode is working here, but if it is not done, I'm not doing it. Now it's working. Okay? Thank you. Because it has been made, that's what I have to carry this, I have to carry a PPT, I have to carry a USB. Life is no good. I know that many times it happens also. Okay, so now what I want you to see that. Yeah, see, sometimes it is tracking that rectangle we have put for firing. Sometimes it is going out. So if you hit, it could be misfired. On the other hand, the proposed one, consistently, you see, it is able to track. So that's what the beauty, which is image-wise I have shown, quantity measure-wise I have shown, and also tracking. Now, granules of arbitrage. I am going towards difficult. That was life was easy. Just you are tracking one card. Now I use granules of arbitrage. There will be any kind of granular series. So what do? I start from a pixel. I make a region going. I compute the similarity, spatial similarity with the next one. Because for every pixel you have got 8 adjacent pixels. You compute the similarity. If similarity exceeds, then you put in the same. If it not exceed, no. That's why you grow. It's called region growing. There is a very popular approach in pattern recognition also, going from the cluster. Region growing. So,
can we take the help of local patterns into the distribution?
What then?
Look, that is 3 by 3 pixel.
Yes.
Can you take the local binary patterns kind of analysis?
What do you mean the local binary? You can say 3 by 3, 5 by 4, 5 by. But when you take one pixel, what are its nearest neighbor?
8 neighbors.
4 neighbors first. 4, which is distance is 1. And when what is the diagonally root 2. Root 2. So you can take 4 and 6, whatever, but you need to cover everything. So you start from on the corner pixel. Corner pixel means only you have got 1, 2, 3, 4. You do not get the other side. So you grow. You grow. Every pixel you grow. When you say no, stop it. Okay? Then you come from the boundary one. You start another one. So then you will get overlapping. That means you are taking more time to extract the arbitrary shape, and it is overlapping. Now here I use RGBD. I take a kinetic data set, which has got another feature called depth feature. Depth feature you are taking because when you are measuring the depth of an object, if it is moving, depth will change. Static, depth will remain constant. So if you take the difference between frames, all static images will become 0. It's called the object extract modeling. But most of the literature techniques called their make it background modeling. You model the background, then you subtract from the image. But we do it other way. So we use neighborhood granules. We use 3-dimensional spatial temporal, 2-dimensional spatial, 1-dimensional. And you would,
How the depth is calculated?
depth is given by the RGB data. There is a Kinect data set, Kinect camera. They compute the RGB and also depth. That is a sensor issue. That is not our issue. That data is available. Initially, when we started working, only black and white. Then over module, we cannot do much. Then we have color. We could solve many things. Then we say color is not enough when you compute. The depth is much better. So it's a sensor technology. That's why it became so popular over the last 2 decades. It's all sensor. Sensor is a very good sensor. It solves many problems. Our research is to, when you have a problem, let us solve it. That's why in the practical case, you may not use this algorithm because you have better sensor, you can, is happy with this one. Okay? So, what is our beauty of this work? We make granule. We do not work on the pixel by pixel. We extract granule, so we reduce the computation time. We use lower approximation as an object model. Instead of background, we do one approximation. Granular level rule generation, automatic updation of rule base with flow graph, and deals with ambiguous tracking like overlapping patterns, newly appeared object, multi-object. So what we do, before that I give you a small of what is neighborhood. Yesterday I explained of a granule that you take a pixel and you compute its similarity with size. So delta is a distance function, phi is a threshold dependent on the one, shape and size of the granule depends, determined by P norm, that is the distance function. If it is a distance function power 1 or 2 or 3, and the phi threshold. Granules defined here around the point xi with this neighborhood are overlapping. Because every point you are considered granule. Unlike Power graph set, a data point may belong to more than one granule. In Power graph set theory says, one point only goes to one. Granular crisp. But here you consider granules are overlapping. Yesterday I mentioned the real life problem, granules are not necessarily crisp. So one granule does not solely represent only its constituting points. Granule has its own constituent points plus other points also. So this is the way we explained initially, yesterday also explained. The regions growing using color and spatial. I take a pixel, I consider color similar. Color means intensity wise. Color means depth wise. So I get RGB and depth wise similarity. I get 4-dimensional images now. So this is a typical image. If you have the if you have the frames of images, you compute the difference. So every point you have an AM, N, and this change of information increases. Change of information is increasing. This is now my temporal domain. And now here I can compute the median. You take for every point Mn, you compute the median. You compute the median. So I get the median, and median is a robust statistical approach. If you take the median, it is much more robust than the data. So I work in the median plane. Now next question comes, hello, no talk please. What is lower approximation of object? Yeah. This lady is doing exercise. Are you just sleeping or fighting? Current frame FT. T-1 movement. So I take the difference, absolute difference, I get. That means this is the portion which is moving. T-2, another previous frame, I get this. Another previous frame, I get this. So with respect to current frame, I have taken 3. If you take 4, 5, you will get more information, but it will be expensive. Now out of those, I take union and intersection. The intersection comes this union out of those. So intersection means this portion will obviously belong to the moving region from F3 minus T to F. Right? So I call it lower approximation. for which for those pixels, code values, I have no doubt. Considering these 4 frames, if I say the 4, another previous, then it will be changed. And I consider this as the upper approximation. This also belongs to this set. That means this is the core region of RGB, which are computed in depth space, and they can be allowed to grow up to this. Though I do not know this, but I only work this. So I compute this over the median plane using depth information. Suppose this is the median plane using depth information. Then I have got, this is median plane, previously tau p, tau 1, tau 1. So here I form all these spatial color granules. Some granules are overlapping, some granules are not. And this is the centroid point. I get this 3-dimensional granule, 3-dimensional in temporal domain. So I call it this together called 3-dimensional spatial temporal granules. I guess first spatial granules, spatial color granules, then in the 3rd dimension I take corresponding to them, and again granules I call spatial temporal granules. Similarly for every cluster, we have got this granule. Because they are also we are computing the similarity with respect to some threshold. So you can see that all 3rd dimensional granules you are getting, they are of different sizes. So out of this I compute, I go to the FT domain. This is my temporal domain and this page. I go to FT domain, location is fixed, mm, I compute the same domain. So I get for every of this granule, R, G, B, one component, I get temporal domain, I got depth domain. 3 sets of features, and these are all set theory features. Set of these 2 sets. So I ignore all data points. Now as an example of this spatial color granule, see that the granular form, just for the beginners, how would you like to get from? So then, I'm not skipping. So this is my rule based on experience. That this is complete background, this is complete object. Because all these features, set theory features, with respect to temporal domain, with respect to RGB, with respect to. So I take an unknown image, I consider the granule, and I see for granule, if all these granules, this is set form not belonging, partial belonging, complete belonging, not belonging. So not belonging means the set is exclusive. Complete belonging means it is within the set. Partial belonging means it's covering outside. So complete, so 4 features, not belonging, belonging, partial belonging, and complete belonging. So ideal case, all those features should be not belonging, not belonging, not belonging, boundary. All features should be belonging, object. And these are all physically defined experiences. Because it is an unsupervised. I have no previous knowledge about the data, but I have the experience that when I track, this should be the ideal cases, and these are my different cases. And here will be some, look, 8 and 9, these are ambiguous cases. Same feature. But one of them for background, one of them will be object. So when I fire for an unknown, I want to make sure that these unambiguous rules least fired. If it is more fired, I can define a coverage factor accordingly. And if the coverage factor is low, that means number of ambiguous rules is firing more, then I need to change this feature value with respect to this rule base. That is done by granular flow graph. What is flow graph? I'm not telling one. So flow graph is basically intelligent way of automation of data. What is intelligent? It's neither the ranges of all features for an object, nor the ranges of all objects need to get updated at all. So when I see the coverage factor is low, I find it which feature is important. So then I change only that feature, not the all features. That's why it's called intelligent way of doing it. It is called granular flow graph, and it maps the decision path of the granular flow graph. This is our new concept. Flow graph concept was given by Professor Paula for example. But in our case, we applied it to the concept of granule. We have been considering in the program all weighting factors are set theoretically. So now let's see the object. The lie was doing exercise, overlapping objects. See, it could have been tracked as a one object, but it's intelligent, or two objects. Again, I will read. When you are moving two heads, it could be tracked as a one object, but instead of that, two objects. It's a way adaptation. Now you may ask me what is the effect of program adaptation? If I don't do, the lady who are doing exercise with her right hand, suddenly she starts moving left hand, tracker is not able to track it. So without adaptation. Now if you take it adaptation, so that means if you are tracking one particular object of interest, car or human being something, another comes or comes, then suddenly it can also track that. Now people are moving in different direction, different speed. Frames per second 15, p equal to 6. That means total 1 minus 5 basically. That is 5 previous rate. See the thing? Different color, different color. See, it is reflection. Shadows are not detected because we are using depth space. So shadow depth space is not reflecting the signal. So you see, very interesting. Then in the reflection window, it's a reflection window. The different moving direction in different speed. It came out in our IT transition on the cyber critics, which had a high impact journal at that time. Now, I'm not showing the comparative results. I'm skipping. Now come to higher, even higher, occlusion. You are tracking something, it got occluded. Complete occlusion. So there I use prediction. Earlier case I use rule-based classification. Rule I generated from experience. Because it is unsupervised, this is also unsupervised. Life becomes difficult when it is unsupervised. You don't have no prior knowledge. You have to use your mind. Estimation, previous samples, that's why it's called machine learning. You are using the previous year. So here I use spatial color neighborhood granules. So I compute the neighborhood granules in spatial color domain, just like we did. We define a neighborhood rough filter, which estimates the location and color models of objects. That we have 3 previous frames. I pass it to the filter. A filter gives me for every frame lower approximation, upper approximation of the object. That this portion will definitely belong, this portion possibly belongs. So from these 3 previous upper and lower, I can compute the displacement, acceleration, etc. Then I can use the estimation also in the next unknown frame because I know the tracking. Okay. So this information are used to model the nature of variation in size, speed, direction, so as to locate the objects in the next frame. That means I am predicting. Based on my previous 3 frames or 5 frames, I computed the displacement, acceleration, and speed. Then I think that in this speed, if it goes, suddenly the object changes, then it may be difficult. So I'm assuming they do it in the consistent. Usually that's what we do. When you drive a car, we drive in the similar speed. Or you walk similar speed. Unless you start slowing and then you run fast, then it may be difficult. Object regions with minimum roughness. So every object is characterized by lower and upper. So I compute the roughness and I go for lower roughness. So if it is minimum roughness, I sure track it. If it is high roughness, no. That means the object is obscure. There I use some uncertainty is called intrusion entropy, which makes sure that the border pixels will go to object or background. So I put it in the object, I compute again rough entropy. I compute to 1, the wherever entropy is this, I go by this. So it handles partial one. So what do we do? Neighborhood after incorporates neighborhood information. Since the neighborhood granules are overlapping, they are suitable modeling the overlapping characteristic of data. No need to define the size of granules. This is automatically taken care of. Granules will be automatically formed given feature threshold, and these 2 parameters only required. Now what is neighborhood filter we do? Two types of temporal information we use. I'll just skip it. Yeah. You take FT, just understand. You have T frames, T minus 1, T minus 2, T minus 1. I compute T, T minus 1, T to T minus 2, T to T minus 3. I get 3 frames, temporal domain. I take the union. So I get 1 frame. Now by the same, T1 minus T2, T2 T minus 1, T minus 1 to T minus 2, T minus 1 to T minus 3. So I get again 3 frames. I save this 3 frames. So my input to the filter is T, T minus 1, T minus 2, T minus 2, they are union, 1 filter. That is 1 frame. And another is 3 frames, T2 T minus 1, T minus 2, T minus 2, T minus 3. So two types of different information we have taken. I put it as input. And we put a 1 to P point convolution. You know the convolution is a multiplication, maximal. So it will give you 2 P point matrix. And one is called lower approximation, other called upper approximation. Filter design. So I have input output relation. So I take, and this filter design is a convolution operator. Convolution operator we use union and intersection. If I take intersection, this will give the lower approximation. And if I take the union, then I take those canals with which this lower approximation have non-empty intersection. It is a deep choice by the definition of upper minus lower. So I take whichever is the intersection, I take the data definitely below it, lower approximation. I take the union, and out of the union output, I took only those with which the lower approximation has non-empty intersection. That means they will be the boundary. So I get lower approximation. Great, yes. So this is important. Let me finish and then. You are talking. It's an image frame. Image frame. No. You are taking just image. So now the image frames you just convert. Multiplication. To image frames you are just convoluting. It's a 1 to P point convolution takes place to result in a P point matrix. So this matrix will be 2 representative, one and upper. Because its characteristic, because filter operation is union and intersection. If you take intersection within the P point 1 to P point matrix, you get 1 lower approximation. And now you take the union, you generate 1, but out of those union granules, only take those granules which have non-empty intersection with lower. So that will give you upper approximation. The lower and upper approximation by definition, not intersection. And here all are special colors belonging to delta P and delta I also. So this is a typical image for P equal to 3. 1 to P point 1, you get lower, upper, possible to 3 frames. So out of those I can compute all 3 frames, special displacement, then speed, direction, acceleration, all those. And performance measure of neighborhood filter. What do we filter? I borrowed the idea from one. So it is a signal to noise ratio. You want to have more lower approximation and least upper minus lower approximation. And this is controlled by the second T1 minus T minus 2, T minus 3. And upper is controlled by T2, T minus 1, T3 minus 2, T minus 3. So this is my cardinality of the obvious set, which is called amplitude. This is my cardinality of the boundary set, which is called 1. Lower value of SNM is 4 filter convolution. So what we do? We need to improve it by changing the threshold. Because what we had less number of lower signals. Now when we decrease the threshold, the granule size will be more. Similarly here, we increase the granule threshold, so the granule size will be less. So by adjusting, even if you see that numerator and numerator doesn't change much, then what do you do? You increase the number of frames. Well, based on the 3 frames, you cannot reach the energy. So you need the another frame. That is, you have already. So threshold 1. So this is a London metro. Many people know. The guy is tracking complete occlusion till the tracker is being able to track it. Another guy is moving in different speed. So here you use 15 frames per second and P equal to 6. 1 and 5 meters frame. Prediction. In earlier one, there was no prediction, rule-based classification. This is prediction. This is unsupervised, this is also unsupervised. And a lab image in presence of many objects, statistical, all stationary objects, so they do not get trapped. See, complete occlusion. Overlapping. Because the lower portion is actually trapped. Okay? Yeah. So this is another one. This is long distance, long duration tracking. That guy is little faster, working normal. Okay? So let us stop it. Yeah, right now. I skip little 5.1 intentionally so that I can cover my entire thing.
Take a break for 5 minutes.
Are you listening or you are
फोन लोकल
Students come back fast.
How are you doing? You are attending my talk? No question of living in English. You are a professor. You can enter anytime. You look happy now. Yes, okay, that's why I turned it off. you have two classes. So we just started with anyone. Start working with people. Good area to work. Neural network concepts. So on it. No, not true. We are not free because I have my sister-in-law. I could not go there because she planned she took leave for a hospital for 45 minutes, but still I was quite away. They said, "You have asked me to come." I said, "No." I said, "Okay, I'm going to go." That's why I do not tell anybody. So I got a mail, so they can. Next time I say. The last time also he asked me to buy but he offered me a very good lunch. And they come there and I think that was it. And I left my jacket in the car with a flight. When I came here, I forgot it. I got a phone call from here. I was disturbed. Why is your jacket? Oh, can you come? After I got this, or it come, so I called the boss. He said, "No problem, I'll come." It was not fine. He changed. Yes, when that. Nice one. Really good. all the person who like to go and speak, whether you like or not, one time I got a request from somebody, how did you go and translate?
Attitude.
So, you please remind me, writing is.
Yes.
I mean,
Yes, I.
sorry. So I'm just keeping by. Today, Kanta. In China, they do it in corporate. Same people, na? China, one time is no argument. 0-1 decision. Yes, no. In my country, only. My country. You know why Chinese and Japanese are very good in philosophy? My interpretation. They like systematic. No. Chinese, Japanese, why do even if they get angry, happy, that doesn't appear in the face. Fuzzy, 0.5 members. In our Indian case, the Granular always comes with them. Is angry with the boss. They respect boss and we always ask the question. So I don't ask my Chinese friend. As soon as maybe you are born, maybe ask who is my leader, so that I have to listen to her. In my country, people ask baby, why? Why are we here? Every time we ask why. That's why I say Chinese one. And Indians also very good because if you go to market with that potato, 5 kg, the software wants that one side goes up and you want the other side. So you argue and then you get a solution. You never are happy with the 0.5 kg, 5 kg example. You always want a little more. Because of the potato size, you cannot make it. So India is also very good person. So in China, they say 0-1. No argument. But here, okay, let me begin. So conclusion part is people take out 15 to 20 minutes at least. So I have explained some machine learning tools. These are all machine learning tools developed in my lab. Over the past at least 2 decades, you can see the publication. I have shown application to video analytics, starting from image to one, thresholding, pixel classification,
then different kinds of tracking problem. And also I didn't get this bioinformatics application, video conceptualization, neural network generation, avatar of PhD thesis work. Just like you develop first lower approximation of the data for every class. You grow a simple network. It is very easy. You train it. Then you grow it with the upper minus lower. That means you make it your son first pure, don't mix with others, etc. Then after graduation you say no, you mix with others also. Adapted. So that's how you gain competition time. Social link prediction, your cluster detection, community detection. Social link prediction, it's a Facebook. Today you are my friend, and through your friend I get another friend. So they consider every friend is 0, 1. I consider no. When you are my direct friend, and I become friend to another through you, the membership cannot be same. Membership should be different. Based on the duration, we make community detection. Based on duration, we make the prediction also. That today you are friend, tomorrow everyone. What is the probability that third day you will be absent from a friend, and then I get a new friend. It's a tremendous application to product design, marketing, everywhere. So next question, so where these are leading to? When you do research, you have to keep in mind one. There are certain things, computer theory of perception, natural computing, and big data analytics. So computer theory of perception is when you drive a car, you have the perception of speed, perception of space, likelihood, etc. And perception, since it is because of the limited resolution capability of human brain and other perceptions are imprecise, boundary. So fuzziness comes in. Perception granules, attributes are granules, slightly, more likely, fast, etc. So fuzzy computing can be a tool to quantify, but it is difficult and easy to say. But you can think about this. It's a very good topic. Perception is you are performing tasks based on perception, not by measurement. When you drive a car, you do not measure and then drive. You use your perception. It's a very promising research area. Say for perception of granular, natural language position. Subject, predicate, belief. Flower is beautiful. This is a sentence I give you. So what will be the perception value? Description of a flower, beautiful, and how strongly one believes to be beautiful. Predicate, belief. That means it incorporates two kinds of appreciation. On a level 1 appreciation, what is beautiful? Very beautiful, not so beautiful, more beautiful. And another one is how strongly one believes to be beautiful. Based on our Jade's G number papers, one of our former PhD students, now she is a faculty at IIT Jodhpur, all writes in this term paper. Now, relevance to natural competition, you can work, that's like granulation is process like self-reproduction, self-organization, functioning. So, our granulation is one. So, if granulation is inherent in human thinking, fuzzy granulation, and reasoning process and plays an essential role in human competition. So, natural computing point of view, it has a very significant. The original definition of soft computing by Zadeh, it has fuzzy logic, neural computing, genetic, and pattern. The augmentation of the definition by introducing rough set, it is the contribution from our lab in ISA. And this augmentation enhances significantly the basic computational intelligence characteristics of soft computing, the foundation for the conceptual design of machine learning. Now come to big data. Big data, we all know we need uncertainty handling, granular mining. We have the competition about the big. Now, here comes the question of, it has application for COVID-19 detection, screening, so many papers have come during the past 2 years. Now, nothing is complete if you do not talk about deep learning. We are all on machine learning. So, we introduce the concept of granulated deep learning. What is deep learning? Learning in depth in different stages. In my other previous work, I didn't go learning, just by sample, I learned it. So, it's a machine learning. Now, in a one, I say, if you spend more time, you study more and more features, depth features, which will be invariant and you can give better results. So now the question is that deep learning is very expensive, because it depends on the number of, larger the number of samples, larger will be the efficiency. But larger the number of samples means it will be computational burden. So how to make it reduce the competition? Here comes the significance of my laboratory. We started working. So convolution neural network deep learning. I am giving one example, some introduction. How many of you know about deep learning? That's why we are being little different because you have seen machine learning. Convolution neural network is one of the popular architecture for handling images. There are many architectures, LSTM model, autoencoder, etc. It represents a deep architecture with input, output, and several hidden layers by its convolution, pooling, and reload. I will explain. In deep learning framework, object recognition viewed as a labeling different tasks in an image frame, labeling different objects, and they are with high probable classes, and then predicting their bounding boxes. That is that. So everyone you detect object with high probability of classes, and then put the prediction boundary. It's simple. You have the deep network CNN acts as the backbone to extract features from input image, video, classified to different objects with these features. Just you, in a layman's sense, you think that way after going through this lecture. This is a typical model of deep learning, convolution neural network. You have input, you have this convolution layer, there you use 3x3 mask as you asked me a question someone. Then you have the maximum pool operator, rectify linear unit, the fully connected network, it goes to subordinate to output. So in GDL framework, if you see that, what we do, for every pixel we put a mask, we compute the convolution and roll layer. I said no. Let us make it a granulated in the image. So if I have n by n, 32 by pixels, and if I can reduce it to only n granules, say 10 granules or 5 granules, then I reduce, what will you gain? Only I have a segment. So I make the convolution only for 1 pixel in this granule, and I repeat this same granule. I convolution, I get the output from one of these, corresponding to one of the pixels in this granule, and I call this output convert value, I put it here. So we jump over only the granules instead of individual granules. Therefore, for a 32 by image with n granules, sliding the filter is done only n times instead of 32. Obviously, it will be registered, but at the cost of performance. You have to sacrifice. Nothing is free. Again, I told you which one you give paper priority. Here is an example of this laboratory data. I showed that the two guys got overlapping. Same data, I am showing the result. Granular deep learning with 3x3 granules. That will be standard, as I explained before. This is arbitrary shaped granules. Deep learning with rectangular granules and without deep learning. Let's consider on a CPU that time. So speed, it has increased here from 1.6 to 2.2. With granular deep learning with 3x3 granular deep learning using arbitrary shaped granules. Tracking accuracy. First, second, third, fourth. Speed wise, this is maximum, this is 1, this is 1. Accuracy of detection, 70, 60. So let's see this effect, whether it is acceptable to you compared to this one. Same one, you see. Table chair, all are being in percent, this much accuracy. You see, tracking is, overlapping is taken care of, plus with the percent. So you are not interested in whether it's a lady or man or what. So here what is very fast. And you are getting this, and it is detecting the chair table is very difficult because they are, the way only you have used deep one architecture. That's why chair they have got different, that's why you get poor recognition score sometimes, the chair. People may ask the why you are poor one. I am not objective in the, interested in the background. Now, this is the deep network used not during training, only during testing. But training we bought it from the CNN network for testing, AlexNet. Then during training we use transfer learning so that you have less time cost. So I will only use the, given a trained data, how can I use it for testing? Now I will show another important one, explain granulated region-based CNN, a very popular one, an improved version of faster RCNN for extracting region. So first you extract the region of interest, then you extract map, then you want. So it is a two-stage detector, little time consuming compared to the single-stage detector, but it is performs much better. So already in the market we have got faster RCNN, now we will make it granulated RCNN with spatial color temporal network. Improves performance both during training and testing. So improves time detection speed and accuracy. This is my model. There are 5 CNN models. These are my addition in the model. I take all the video as a direct input. Others they take frame by frame. I take because I am using temporal domain. So I had to use. So what are the array? This is called, we have used Alex network, which has got 5 CNN models. This is the GLXnet classification network. Now what are the differences? Their videos are directly as input rather than static. Spatio-temporal granules for extracting region of interest. Better than fast RCN. We use spatio-temporal granules which are not being taken care of by faster RCN. Only we have used granules formed over the pool map instead of all feature maps. So you see that what are we doing? We are taking the videos and for each frame we are passing through one and computing spatial color map. Now at the same time we are giving all input to here also. We are computing temporal graph. So for each frame we are giving sequentially. Given a frame FT, we compute this, and given a frame this, we compute the previous frame is spatial color, and then you are taking the intersection. So the result is spatial temporal. So I have reduced the number of pixels basically. So I don't have to take the burden of the background, which I am not interested. Then after coming here, after pool 5, I tell another kind of intersection. Whatever I get here, intersection of the pool 5 and this granular 2. So I further reduce. So my region of interest becomes very scanty. Since I have a resolution 1, in case I miss any information, around that I push different masks. Rectangular, color, diagonal. Instead of taking all the pixels, I reduce it first to significant, which should definitely belong. Then to get the better ones, if possible, if I missed, I put around 4 to 5 masks. So each mask represents my input to the support vector fully, and corresponding FT values. So therefore, only the positive ROI, that is ROI is depending on the object, instead of the whole ROI map as input, while retraining the GRC. Because when I use this, I had a trained AlexNet. Now because of the addition, I have to retrain it. So retraining takes time also now. So when I am retraining, I will only use this portion of significant one, not all background. And only FT regions corresponding to those here it is a transform domain pixels, so corresponding original FT values I take as an input to support vector, and therefore improves real-time detection and accuracy. So here I have a trained AlexNet, I modify it, I retrain it, I get this. Very simple concept. Now you see, I take the videos, I see so on. See, it's a granular and training. It's a faster RCNN, granular faster RCNN. 57 by mean accuracy speed. Every pixel with the accuracy speed, I take the mean value. 57 to 78. it is a image data. And you are not, since in image data you do not have the temporal information, only I just considering this portion only, not this portion. Now, next one I consider RPN, video data, spatial data. Video data. Here you see 70.5 to 80. So during training it has improved. And this slightly increases because of the retraining. Since you are training, the retraining. So GRCN is superior to faster RCN in terms of training accuracy. GRCN needs more training time than RCN because of retraining of the AlexNet, additional granulation. GRCN RPN takes less time than GRCN FRPN as it uses only spatial information and does not read granule circle. See, you are interested in that. RPN means only spatial data. FRPN means spatio-temporal. Spatio-temporal take it is little more time because you are computing the linear intersection operation. That's why GRPN takes little less time than FRPN as it uses only spatial information for granulation. It does not need granules 1B 2 layer. GRPN FRPN has higher accuracy rate using additional temporal information. I'm not going into the details, so it's by training result. Similarly, if you go by the testing result of the training one, you compute the result 57 to 62 to 5. First RCN, faster RCN, GRCN, 57, 65, 79. How much improvement? You take another one, training data, AlexNet, 61.3, 63, 80.9. And here the test speed for RCN is 1.4 frames, 1.6 frames. So for faster it is 6 frames. For our space it is 5.5 frames. So it is that way it is inferior to 1 as per the frames per second is concerned. And ROI pixel detected by RCNN are more representation of the object pixel. That's why I told you. Now let's have some real-time data in our steel plant, Indian one of the steel plant. I take first RCN, FRPN and RPN. Now see that we have got car objects like car, bike, scooter, loco, minivan, bus, just in a steel plant what is happening. And car means green color, bike means pink color, person means blue. And I use multi-class detection, the deep shot algorithm, that is a tracker. So my tracking is not done by the DeepNet. DeepNet is only doing the detection. Better is the detection means tracking will be better. So tracking takes care of the other things, how speed. So you track 5 and then you leave 15. 15 will do the same path. If there is error you correct, then again. That's why tracking speed increases much. It is not dependent on much on the detection speed. So look at this one. High speed coming. See, color was I telling you about. Car, bike, scooter, loco, minivan, bus, truck, cycle. This is my faster RCN. You can notice that some of the objects are not being tracked. Look at it carefully. Some of the, oh yes, that man is not being tracked. That man is not being tracked. See, this bike was not tracked. There are many. Now if you go by the next one, RCNA. First RCNA, sorry. GRPN. That means you are using spatial color granulation only. Now you see that red color were not detected by the previous one. So I marked by the red color circle, which were not detected before but is detected, getting detected. You see red objects. Red objects. Yeah. Their additional detection. Now let's go to the FRPN. Now go to FRP, that is you are taking spatio-temporal, maximum. Now see that which you are not been able to detect by spatio color, now they are getting detected. Again showing by the red mark. So you see that here FRPN is superior to spatial color in terms of both MAP score and FPS, frames per second, as the former uses less but effective, because number of point detected was mine less, but they are effective. And anchor for classification, this drastically reduces the time in spite of using additional intersection operation. So here again I am telling you, I have used granulation to reduce information which are not required to be. But I have kept the salient ones first, and then I have extended it to some possibility that so that my others are not getting mixed up. So that, by the way, even I put some additional information, but my completion time has been superior to a spatial cover. So this last part is evolution. Now if you look at the evolution, we started working patterns in 1960s as per the literature. We started in 75. MS Post in 1970s, every 10 years subject came. AI ML expert system 1980s, knowledge based system 1990s, data mining 2000, big data 2000, now we call it deep learning and analytics. So every decade we are changing the topic because of our requirement. And every time we have the data different one, mother subject pattern recognition gets updated. And technology also gets changed. For example, new approaches for different tasks to handle. For example, teacher selection problem, when we started working in 75-1, our number of sample was few hundreds, teacher was 2 to 3. That time, how to find the best teacher? Because that time teacher selection problem was not that important. The number of teachers only 2 to 3 or 4. So you find those features for which you cluster the sample space and see where the separability is maximum. Very simple, we publish paper that time. I can transition. But now this cannot do. So now number of sample is very small. And number of features is you found it. Bioinformatics data, number of genes, 600, 2000, 4000, 5000. Number of samples, 50, 10, 60. Because you go to hospital with the worm only when you're sick. And number of samples in the cancerous growth is more than the normal. So then how to use it? So there lies the question of this paper, highly cited paper from C.M. Murthy and myself. It's a 2002 paper, highly cited paper. That if you see these features are uncorrelated, you cluster within the feature space. And if you have few thousand, you can reduce it to few hundreds or few tens. Then these are my reduced, and then the centroid point of this cluster, these are my reduced features. Very fast and very efficient. But it is, features have to be uncorrelated. Just like you have the natural, exactly heterogeneous data. That's why big data and the database is becoming popular to handle heterogeneous data. So new terms and technologies coined with a big hope. When neural network came, we had long hope. Every problem can be solved by neural network. But after 7 to 8 years, subject lost interest because we expected too much without contributing to the science. We do not bring out when it is only multilayer perceptron, ONN network and few platforms. We expect that they will do miracle. No. Subject was lost. Again now deep learning came. We have lots of hope, deep learning. So we should be very careful in jumping to deep learning. Don't jump. That I've been telling for the past 5 to 7 years. If you want to learn deep learning, you have to learn shallow learning. You have to learn shallow learning, you have to learn neural network, must. Because this is a best candidate for machine learning. You learn for machine learn for it. If you want to learn artificial neural network, you have to learn pattern recognition. Unless you know the characteristics or challenging issues in classification, clustering, feature selection, your neural net cannot help you. Unless you know that, you cannot develop in this system. Unless you know artificial neural net and its drawbacks and limitations, you cannot go for deep learning. That's why yesterday I asked question, why should I go for machine learning or deep learning? I said, if you can solve your problem, machine learning, why go for deep learning? Deep learning means you are learning in depth and depth and depth. So that in machine learning basically is trained for particular task, one task. But deep learning has bigger objective. You learn the features so that you can handle similar tasks. So you know how to learn a new task in the rules. This is the basic difference. So data-driven science research summary, it concerns with the acquisition, storage, retrieval, processing, reasoning, mining, and finally the conversion of data into knowledge. Unless you conversion, there is no question of doing data mining. Because common man has to understand in his or her own language, natural language. So it is a huge challenge. Employs techniques, theories drawn from several fields like mathematics, statistics, information science, computer science, highly interdisciplinary. And application of domain knowledge, where you using the domain knowledge is most important. Otherwise, doing theory has no meaning. Therefore, it is multidisciplinary. It has potential for R&D perspective, both in academia and industry. In India, scenario is extremely encouraging that you must be facing that if you do computer science, you get a better job. 1 lakh. If you do mechanical civil, you get 50,000. I do not like this. I do not encourage this. But I see that it will go. It will take them. But again, it will change. Let me tell you. If I am surviving, then if I meet, I will tell you. But if I know it's a demand, because same happened in neural network. So I hope whatever we had faced in neural network in 80s, and we are working on machine learning based on previous experience. So use those previous experience so that you see similar bad situation does not recur. Does not recur. Otherwise, you're spending so much time hunting codes and chains. After 10 years, you say, no, you are not doing anything else. You are just only doing coding and you are expecting too much on CNN. Okay? With this one, I conclude, acknowledge my students. Most of the work of my students and junior colleagues. I didn't work with big professors. National Science Chair, ESC Institute Chair Professor. So, I don't no advice. Thank you. These are my These books in public give you family. That is the contribution was of Devadosi. I was changing a day, let's write a book. This is the high time. We completed the book. This is another book, Foundation Software, with my Hong Kong college, Chinese college. There's some Professor Flickr Link, IIT professor, is an outstanding pattern algorithm for data. That's how I define data mining from pattern recognition point of view. You should make your subject in your way. Let others follow you. Don't follow others. Let others follow you. This is Shambhu Mitra, myself, who is our director. This is my another colleagues, Pavitra Mitra, Bhartaji. Please stay safe and keep well. He has also one book on neural network, Spinja, but it is not relevant here, so I didn't put it. Chengdu. If you get time, you go to China, the Chengdu, there is a research base of Panda. Panda is very expensive, very sophisticated. The air condition, they live, they are all small bamboo, you already have to see it on this case. Red panda, they can stay other way. But this panda is very expensive. Very cute. Yeah, very expensive. Air condition, Thank you very much. So, I quit that. Any question or what?
Any questions?
Anything you would All of you.
Thank you so much, sir. Thank you, AICT. Thank you, Professor Shankar Kumar Pal, for coming all the way from Kolkata. We are fortunate enough to meet with such a great personality, great researcher of India, Padma Shri awardee. We are really fortunate to see you here, sir, and to hear your lecture, sir. Thank you so much. Thank you all the participants. Hope you have got some direction and you have learned some concepts first time. But if you will further work on that, you will learn a lot. Please study the research papers, whatever the great works people have done. So whenever you want to identify a problem, first of all you need to read the literature. That how far people have worked, then only you can find out on which problem I need to start my work. And most of my student participants are from CSE AIML department. So I hope they might have gained a lot, and data science students are also there. So though it is bit high standard for them as a beginner, but I hope they have learned some buzzwords, they have learned the definitions of soft computing, what is machine intelligence, AI, what is granular computing. So they have understood the concepts of clustering. So all these concepts will help you a lot in your career and future. Thank you so much, sir, for your valuable time, for your informative lecture. I'm very glad and I'm very honored, sir. Thank you on behalf of IARE, management and all the participants. Thank you so much.
Friends, your physical attendance will be taken. Madam has come. Please keep quiet and
Legal attendance.